This video will lead us through a discussion of the titration of polyprotic acids. If we just conceptualize what's going on here. So we're beginning, for example, the example problem that we'll work with deals with this diprotic acid. So it will be the major species to begin with, along with water. As we are titrating it with hydroxide, that diprotic acid will be in the greatest abundance, so the hydroxide will of course react with it, and because water is one of our products, it will be far favoring right, and we will be creating the conjugate base of this diprotic acid. Well, as we're titrating and removing this, we know we're making more and more and more of this. So if we want to imagine our pH curve, now being a weak acid, probably before the titration begins, we'll start, depending upon the strength, about 2-ish or 3. And then we know when we first add base, the characteristic of a weak acid strong base, we are going to jump in our titration pH and then begin to level out. Well, if we want to identify that we're starting mainly with this diprotic acid, and as we first react it away, well, we're going to be diminishing the concentration of this and increasing the concentration of its conjugate base. Well, eventually, we'll reach a point where these are equal, just like our monoprotic acid. And so at that point, the pH will be equal to the pKa1. So remember, the release of the first ionizable hydrogen we would describe with Ka1, but then this has the potential to continue to be an acid, so Ka2. But then as we continue past halfway to the equivalence point, we'll get more and more and more of this conjugate base, but still this acid, and then eventually we'll reach the equivalence point where we just have this Ha-. So let's just talk through how we would, problem solve up until that point. All right. So to begin the titration, what I'm asking us to do first, back to our class packet, is we are going to titrate 100 mils of 1 molar phthalic acid. Here's our Kas with 1 molar sodium hydroxide. Okay, so what is our starting pH? We have not added any of our titrant, so we only have to consider the first ionization of our stronger acid, which will be the molecular form. If this is our major species, then we just have to consider an ice table. So we'll be starting with just 1 molar of this. We're applying Ka1, 5% rule checks, and our pH to start. This is a fairly stronger weak acid, 1.44. Okay, the next portion of the problem says after we've added 25 mils of hydroxide. Okay, so our titration begins. So from the start, our hydroxide, 25 mils of 1 molar, so we'll have 25 millimoles. And we're starting with our diprotic acid. I'm just going to represent it as H2A, and that will be 100 millimoles. And we know a full drive to the right because we're making water and then some of the conjugate base. Okay, we are not at one of our benchmark spots. We're not halfway to the equivalence point. We're fairly in, so we're going to have to go through the full ICF. And then this, of course, is limiting. So we'll have some of this remaining and some of this. So it will act as a common ion problem for our diprotic original acid. So I've done the work here. There's our ICF. Just be careful of sig-fig operations. Our volume at this point in the titration will be 125 milliliters. It yields these concentrations in solution, and then applying the Ka1, because this is still considered, our reactant drive. And our pH has gone up to 2.41. All right, next point in our titration. So, 50 mils of hydroxide added. Aha, we are halfway to the equivalence point of this first acid. So, just like we learned last chapter, we can apply this guideline because we know that we'll have the same concentration of the diprotic acid and its conjugate base. So in the Ka expression, those concentrations will cancel and pH will be pKa1. And so at this point, halfway to the first equivalence point, that will be our pH. All right, so where are we next? When we've added 100 milliliters. Okay, so we're at the first equivalence point. The hydroxide has reacted all of this original acid away, and we just have the HC8H4O4. All right. We really have to be cognizant of how these different species that we are creating will act. So, none of this remaining, none of this remaining. We just have water. We'll of course have some spectator ion from the hydroxide, but now we just have this. And I know we are just going to think, okay, it's going to act as a base. Oh, but it has an ionizable hydrogen. And there is nothing in the environment that's going to force it to just be acid or just be base. So it is going to act as an amphoteric anion. We're going to see both behavior. So we know how to deal with that. That is where we apply the equation of pH is pKa1 plus pKa2 divided by 2. And so the pH here is 4.15. So our benchmark, whenever we are here, this is amphoteric. If we are titrating a polyprotic acid, at the equivalence point, we have to be careful about what we're making. Okay, so let's consider the rest of our titration. So as we move from here, now when we add hydroxide to this, that is going to force this amphoteric species to behave as a base because that's going to form water. So it's as if we're starting the titration of this. So we're going to get a jump in pH. We'll level out because as we're reacting this, we are going to be making some of its conjugate base. Halfway to its equivalence point, we'll be able to apply the relationship of pH equaling the pKa2. Then as we go beyond that, we'll make more and more and more of the conjugate base and less and less and less of that acid. Eventually, we'll react all of that acid away and we'll just have the A-2. This is not amphoteric. This is base only. So to deal with it, we'll have to handle the calculations with Ka2. But then beyond that, we'll just have the hydroxide remaining that will dictate the pH for us. All right, so let's dive into our calculations. So, we are picking back up where we are at 125 total mils of the hydroxide, so point E. Okay, so if we're always referring back to the original acid, we started with 100 millimoles of that, and at this point, we're beyond the equivalence point of this. So this becomes our limiting reactant. We will react away 100 millimoles of both this and the base, and have made 100 millimoles of this amphoteric anion. So this is gone, but I have 25 millimoles of this remaining and 100 of this. can we make more water? And of course we can. So now the hydroxide will react with this. And as I said previously, it is going to force then this amphoteric anion to take on the role of acid because we make water. So, now of course you wouldn't have to do 2 ICF tables if you can just see how much of this will be remaining and then how much past the equivalence point that you've made, of course, of this behaves like an acid sometimes, behaves as both a base sometimes, of your conjugate base of this first acid. But of course, it should be the same millimoles that you began with of your diprotic acid. So, you don't necessarily need to do this if you can just think through and come up with these correct values. So, I have the rest of my work shown here. So, this would be the ICF table with the hydroxide reacting with the conjugate base, or now our second acid. Now we're at 225 mils. Need to correct my sig figs there. But we're just constricted to 2 sig figs and then 3 for our concentrations. We then plug in. We'll use Ka2, and there's our pH. All right. The next asks us to be 150 mils in. So that would be halfway to the second equivalence point. And then we would just take the negative log of Ka2. And there we go. And the next point, it would be the second equivalence point where we just have just base. And we've reacted away all of the hydroxide, the second acid. So this will be the concentration that we move forward with. In the ICE table, we will need Kb2. So you will take Kw divided by Ka2. And then there's our pH. Now there are several titration curves that I have on the following pages. And so this gives kind of another representation. So here, halfway to the equivalence point, and then our first equivalence point, we're going to have the amphoteric anion, are halfway to the second. And then, we're not going to, this would just be, our conjugate base. And so we would just be applying, it would be, Kb2 that we would find by taking Kw divided by Ka2. We could have a triprotic acid. And so that's what this is talking about. And on the previous page, here is if we had a triprotic acid. Here then we would just have the base that would be Kb3 that we would be dealing with. Okay, ladies and gentlemen, you are fully equipped to be able to interpret pH curves, to be able to do calculations as we're titrating. Best of luck. Have fun with the titration of polyprotic acids.